Today, we're gonna discuss about work, energy, and power. When we think about work, you'll probably think about a job, spreadsheet, and others. However, if you're studying physics, work has a different meaning.
Work is defined as the force acting upon an object to cause a displacement. It is expressed as the product of force and displacement in the direction of the force. The formula for work is W is equals to F multiplied by D, where W is equals to the work, F is equals to the force, D is equals to the displacement of the object. The unit of work is Newton meter or joule. 1 joule is defined as the amount of work done by a force 1 Newton when the displacement is 1 meter. We must remember that the work is a scalar. It can be positive or negative.
When both the force and the displacement are in the same direction, positive work is done. When force acts in a direction opposite to the direction of displacement, the work done is negative. The sign on work is very important because it will tell us if the speed of an object will increase or decrease as the result of the applying force.
Angle between force and displacement is 180 degrees. If force and displacement are inclined at an angle less than 180 degrees, then work done is given as W is equals to FD cosine theta. If force and displacement act at an angle of 90 degrees, then work done is 0. Necessary conditions for work to be done. Two conditions need to be satisfied for work to be done. First, force should act on the object. Second, object must be displaced.
Here's an example of work done in a real-life situation. Lamar Grant, U.S. powerlifting star, became the first man to deadlift 5 times his own body weight in 1985. Deadlifting involves raising a loaded barrel from the floor to the position above the head with outstretched arms. Determining the work done by Lamar in deadlifting 300 kilograms to the height of 0.90 meters above the ground. To solve this problem, we need to use the formula work is equals to force times the displacement. We are given 300 kg as our mass and 0.9 meters as our displacement. To solve for the work, we need to find the force first. The formula for force is equal to mass times the gravity. Let's multiply the mass 300 kg to 9.8 Newton per kilogram. We would get 2,943 Newton as our force. Now we could solve for our work. Let's multiply 2,943 Newton times 0.90 meters and we will get 2,648.7 joules. Here's another example. Little John pulls his loaded wagon 30 meters across a level playground in 1 minute while applying a constant force of 75 Newton. How much work has he done? The angle between the handle of the wagon and the direction of motion is 40 degrees. To solve this, we're going to use the formula work is equals to force times the displacement cosine theta. We know that the displacement is 30 meters while the force is 75 Newton. For the degree of the angle, we're going to use 40 degrees. To solve for the work done, let's just multiply 75 Newton to 30 meters, cosine 40, and we will get 1,724 joules.
Energy. The capacity of the body to do work is called energy of the body. Energy is measured in joules. There are various forms of energy, and these are the potential energy and the kinetic energy.
Kinetic energy. It is the energy possessed by a body due to its motion. The kinetic energy of an object increases with its speed. Kinetic energy of body moving with a certain velocity is equals to the work done on it to make it acquire that velocity. The formula of kinetic energy is Ke is equals to 1/2 mv squared, where the Ke is the kinetic energy m is the mass, and v is the velocity.
Potential energy. The energy possessed by a body due to its position or shape is called its potential energy. The formula of potential energy is PE is equals to mgh, where PE is potential energy, m is mass, g is for gravity, and h is for the height.
Here's an example of energy in a real-life situation. A 60-kilogram skier is at the top of a slope. By the time the skier gets to the lift at the bottom of the slope, she has traveled 100 meters in a vertical direction. If the gravitational potential energy at the bottom of the hill is 0, what is her gravitational potential energy at the top of the hill? If the gravitational potential energy at the top of the hill is set to 0, what is her gravitational potential energy at the bottom of the hill? To solve this problem, we're going to use the formula PE is equals to mgh, in where our mass is equal to 60 kg, gravity is equals to 9.8 meter per second square, and our height is equals to 100 meters. Let's multiply 60 kilograms to 9.81 meter per second and 100 meters, and we will get 59,000 joules or 59 kilojoules. Now that we find the gravitational potential energy at the top of the hill, let's find the gravitational potential energy at the bottom of the hill. To do this, we're just going to put negative 100 meters as our height. Since nothing really changed much in our equation, our potential energy at the bottom of the hill will be negative 59 kilojoules. Here's another example. A car is traveling at a velocity of 10 meters per second and it has a mass of 250 kilograms. Compute its kinetic energy. To solve for kinetic energy, we're going to use the formula 1/2 mass times velocity. We are given 250 kilograms as our mass and velocity as 10 meters per second. Let's multiply 1/2 of 250 kilograms and 10 meters per second. And we would get 12,500 joules.